So have all the fellows joined in? Um, anybody who hasn't joined in from your cohort, folks? Let's do a quick check and post in the chat maybe. I think we should be good to go. Let's start it off.
Okay. Should I start? Good to go?
Yeah.
Okay. All right. Hello, everyone. Welcome to this session, 1 hour session on IPFS and the basic concepts behind IPFS. We're so glad to be here, and I hope you're going to learn lots of new things in these hackathon and these days. So we decided to start the session by discussing a little bit what is content addressing in IPFS, because content addressing is one basically of the most fundamental parts around which the whole system and architecture is building on. So my name is Yanis. I'm a research scientist at Protocol Labs, and in particular in ResNet Lab, the Resilient Networks Lab, where we investigate topics related to many of the protocols that Protocol Labs is supporting and building, and we're trying to find solutions. We're trying to see a little bit further ahead in the future and try to solve problems that the systems are going to face, are potentially going to face further down the line. So yeah, so this is the brief agenda for this part. So for the first kind of 20 minutes, so I'll try to keep it a little bit shorter, and then we're going to have Alfonso going on into other things that I'm going to mention in a bit. So we're going to start by why we need content addressing and why we think it's very important for the next generation of internet protocols. Then we're going to go in more detail and talk about how chunking is done and how chunks are linked into Merkle DAGs in IPFS. And then we're going to see how what is the IPFS CID, the content identifier. This is the most important part of the whole architecture, as I said, and therefore we should pay some attention to it upfront. So why location addressing fails us, or why content addressing is important? So this is just a little bit of motivation. There are many more reasons why we should move from location addressing to content addressing. But some of these are that when we have content that is stored in some CDN, then when this content moves from one CDN to another, from one storage point to the other, then the previous link that we use, the previous URL that we used, is not valid anymore. And in many cases, this URL has already been distributed and shared with many other parties that when they click on it, basically it goes to a 404 error and the page is not there. There are security implications as well. In the current kind of location addressing or host addressing model of the web, what happens is that we secure the channel between the two hosts that are communicating and not actually the content itself. This means that malicious users can either cheat the DNS and point to wrong wrong content, and most importantly, that the user cannot verify themselves that the content they're receiving on their screen is actually what they asked for. So we see lots of attacks where you go to a website, it looks very familiar and very similar to what you're interested, what you've seen before and where you're heading to, but actually it is not. You know, there might be some small difference in the URL that the attacker might have imported into the DNS, and therefore you're redirected there, and obviously, you know, you can get compromised this way. There is also resource-based arguments where, you know, there is no content request deduplication or aggregation, as we call it. So if we're sitting in the same room and we request for the same content, say this set of slides, then the network is going to transport the same set of bits twice from the server where they're hosted to our machines nearby. So it's not easy to basically achieve multicast, and that has been a struggle for decades in the networking community. So this is briefly how it works. When we have location addressing, we ask the DNS, the domain name system that we are connected to, most likely the ISP that we're connected to, or the organization. Sometimes, you know, the university or company that you're running might have their own DNS resolver. And where we are redirected to is the server that this DNS machine knows that hosts the content that we want. And this is obviously given by the URL. So you give the URL and you get back the IP that this specific machine knows that hosts the content you're looking for. However, it's very common that we all consume content, of course, yeah, and therefore one file stored somewhere might have been downloaded in many other users that are much closer to you. So what we want to do with the content addressing model is not ask for a specific address of the host that the DNS knows, but basically ask any host and choose the closest one to get the content from. So in this model, what we have to kind of get our head around is that we're not resolving content by its address, but by the content itself. In our case, this is a fingerprint of the content, which we're then asking the network, where can I find this content? We effectively go from a model where we have example.com up here to something that looks something like the one in the bottom. So we have this QMW string, which is the hash of the content itself. So this means that if the content changes even a little bit, the hash is going to become something totally different. And we're going to explain the reasons why this is a desirable feature. So the CID is the content identifier. I'm just going to cover this very briefly here, and I'm going to go later in detail. As I said, it's the most fundamental ingredient of the IPFS architecture. It is used to address content, and it is self-describing. It describes directly the content that you're looking for, the document or the web page. Now, in short, you can think of that. Here is two examples, CID version 1 and CID version 2. You can simplistically, for now, think about it as the hash of the content that you have, together with some metadata packed together in one thing. This offers a few advantages that I'm going to mention as we go through the presentation. One is security, because the content can be authenticated by the address itself and not by some external certificate authority or anything else. It guarantees immutability, which means that, as I said, even if one single bit of content changes, then the hash is going to look something totally different. And you have deduplication as well. So because the same two copies of the same document, they're going to look exactly the same, then you don't need to download things twice if, by clicking the same link twice. So here is a rough breakdown of the system components of IPFS. And in this presentation right now, we're going to be covering the content addressing system. Then Alfonso is going to talk about the content discovery and routing system. And finally, then he's also going to cover the content exchange. There are some additional features and modules that we don't have time to cover today, but we're happy to answer questions and follow up later. So let's get into it and talk about chunking and how then we link chunks in Merkle, DAGs, and so on. So chunking, what is chunking? Chunking is when you get a file, a big piece of content, and you break it down into smaller parts. I'm pretty sure that many in this audience will know that this happens as well in IP networks. And in IP networks where you have IP fragmentation, and we know that the network layer is transporting very small pieces of data of 1 kilobyte roughly. This makes it easier because for several reasons, because if you have errors, for example, you don't need to transport the whole file again. So this is the three reasons that specifically in IPFS chunking is used. It's deduplication, piecewise transfer, and random access. So it's important to remember that each one of those pieces that are broken down from the bigger file, each one has got its own address. So there is the hash of each one of these that becomes the address of the content. So what can we do with this? We can do deduplication. So if two parts of the file are the same, then these are represented by those green boxes here. We don't need to go and fetch these things twice. We don't need to store these things twice, and we don't need to ask from the network to send us these things twice. We can have piecewise transfer. So if some part of the file, in this case, this orange part here, is received in error because of some error on the wire or the wireless link, then the error is identified and we don't need to transport again the whole file. Instead, we can just ask for this small piece of data, and that's what the network is going to send us back. Finally, we have random access. So what this means is that when you want to, for example, watch a video on YouTube, which is 1 hour long, but you're just only interested in the last 10 minutes, you don't need to download the whole 1 hour and then jump to minute number 50 that you're interested in. Instead, what you can do is just jump directly there, and that's only what the network is going to transfer to you. So there is huge bandwidth optimization, as you can understand. So this is chunking very briefly. Now, let's go to linking chunks in Merkle DAGs. So let's see what is a Merkle DAG very briefly. We want to, as we said, we have files that are split in chunks, and those are then, they're not living like in memory just independently of each other, but they're linked in what is called directed acyclic graph. So every chunk is represented by a node, and the way that each chunk is linked to other ones, you can think of it as a tree where every chunk, every content address is one node in the system. Of course, because every node has got, as we said, every chunk, and therefore in this model, every node has got its own content address, it can be requested independently of the rest of the file. Now, let's see what is how we do the Merkle DAG in IPFS. So we have the same file as we had previously with green and orange and blue boxes, and we have those bits, right? So we have, or bytes, we have from 0 to 350. So we split that in some fixed size chunk size. And here we have the green here is 0 to 100, the blue is 100 to 200, and so on and so forth. And what we realize is that, as we said, we want to do deduplication between the two green boxes because they're the same, and we don't want to have them identified differently. So what we do is that we link the bits from 0 to 100 and from 100 to 200 into the same piece of the file. And then this is going, of course, 100, 200 would be the blue, and then the orange one. And this is what is the Merkle-DAG for this very simple file, very small, like 3-chunk file that we have. So Merkle-DAGs are basically data structures where each node is content addressed. So we have these different parts of the file, they have their own address, and therefore we can request them and fetch them from the network independently. Now, to this, what helps is what we call IPLD. So IPLD stands for Interplanetary Linked Data, and it's a set of IPLD basically is a project or like framework that provides the standards and formats to build the data structures in terms of the Merkle-DAG that we just described. So basically with IPLD, we have data, and from data we go to data structures using IPLD. So with the tree-like structure that we talked about before, you can think of every node in the IPLD graph as the, sorry, not every node, but the whole tree in the IPLD graph as the tree of folders that you have in your operating system. So you start from the root folder, which is your, say, user folder, and then goes into all the different folders, and every one of them, they have files and subsequent folders in them. So it's something, you can think of it as something similar. And when you want to transfer, like to copy a file from one folder and duplicate it to some other folder, basically the operating system, what it does, and similarly what IPLD does, is that you don't need to copy the data and have it twice. Instead, you put a different link that connects the folder to the part where you wanted to copy your file into. So what does this give us? It takes us from location-based addressing to content-based addressing. So you get this URL, which in IPFS terms corresponds to IPFS : and the hash that follows there. So this is a very powerful thing because, as we said before, it's very few or only one host that can actually serve this URL here, as compared to this one that anyone with the content can serve it back to you. This is because, as I said, this points to one IP address, whereas this does not point to any IP address. It points to anyone, it points to the content itself, and therefore anyone with the content can basically send back the file. Now, let's finally get into the IPFS CID part, which is a kind of combination of several of the concepts that I just mentioned that makes the content identifier used in the IPFS architecture. So the slide from before, you have these two different CID versions. We don't necessarily need to pay attention to the difference, it's just two different examples. And what they are composed, so this long string of letters and numbers is basically decomposed into these three main parts. You have, which are also shown down here. So you have the multi-hash, which is a self-describing hash digest. This means that you get the content that you have, you apply a hash function to it, and as a result, you have the hash of that content. Now, this is not called hash, it's called multi-hash because it's not only what I just described from the document and the hash and the result, but it also includes the version, like the function that you're using to hash the content. There are many different hash functions, and therefore that's why it's very important to include which function you actually use to hash the content. Then you have the multi-codec, which is a non-magic number that identifies some format or a protocol, and we're going to see a table of that in a minute. And we have multi-base, which is the base encoding string, basically. So here is the table, well, part of the table of multi-codecs that exists, and you can find the rest of them, like the whole full list, in this URL on GitHub. And as you see, you have a name that identifies, what is it that we're trying to do here, like to represent. And this is the code by which it is represented. And you can see that you can have several different things. You can have protocols like IPv4, like very common protocols that we're using, or DCCP. And you can also have serialization formats like protobufs or CBOR. And these have the different codes in this system. And you can use that universally, like you don't use one instead of the other. So you can use IPv4 together with protobuf if you want to say that the serialization format of what we're just about to talk about is in protobuf, and we're going to use IP version 4 protocol to transfer this over the network. Now, the multi-hash, as I said, is a self-describing hash digest, where you have the hash digest, as I said, the result of the hash function, the length that you have, the length of the digest, as well as the hash function itself, which is itself a multi-codec. So you can have SHA-2 or 3 or 1 or whatever that is represented by a code here. And this is also included in the multi-hash. This is very important because if you send a raw hash on the other side of the channel, then the other side does not really know how to what to make out of that, how to which function it should apply to some content in order to arrive to the same hash function. Finally, we have multi-base, which is as I just mentioned, the base encoding. And it's basically the multi-base prefix, and then there is the encoded data. And all this, sorry, let's go back 1 second, forms this CID that we have here. First, we have the base, then the CID version, multi-codec, and the multi-hash. And if we go even further back, then we see that it results into something like this, which is the very long string. Let me go forward. Okay, one more. Now, yeah, I mentioned before that there are several different benefits by doing content addressing. And some of them are, one important one is integrity checking. The other one is caching and deduplication. And with integrity checking, it is important because you can go from a kind of trust-based system in today's internet, where you have to go to the DNS and you have to trust that the result that you're going to get back is indeed the result that you're looking for. So you're placing some trust into this entity there to not play bad games with you. With by having a hash-based content address, you can do this for yourself. So you can check whether what you have received is actually what you asked for. And we're going to see how in a minute. Now, caching and deduplication again means that we've seen deduplication. We've seen that you don't need to ask for the same things for the same thing twice or more times, but it's also caching. Caching means that if I download some content from the network, then what I can do is reprovide this myself. Everyone is going to ask in the network with the same CID, and therefore I can identify that, I have this as well, so I can provide it to you. So this, as you understand, especially for popular content, makes it much faster because many peers in the network can actually contribute to serving the network. And this is good both resource-wise and latency-wise. Now, the integrity checking, a quick example here to show why we actually need to place zero trust to the ISP or the DNS system is that because you can imagine you have this document, which is the data, you apply some hash function and you get this fingerprint, which is, as I said, the CID basically. Now, this is what you send out to your friends or whoever you want to link to send this document to. And what this guy is going to do is going to ask from the network these fingerprints. They're going to request the content from the network using these fingerprints, this hash digest. Now, the network is going to send them back the content, and what they can do is they can apply the hash function and see if the result is the same as the one they have requested for. This means that if they match, then this means that indeed what they asked is what they have received. In contrast, if they receive something from the network, they apply the same hash function, and they see that what they have received is different to what they have requested, then they know that something is wrong here and someone tried to send them something wrong. Or maybe even the network, there could be some network error and they receive something different. So therefore, that's not good. They have to throw it away and check it and request from the network again. And this concludes the first part. Thanks for watching. We covered the basic concept of content addressing that is very fundamental in the IPFS system. And we introduced the content identifier, which is used in basically everything you do with IPFS, requesting content, serving content, and so on and so forth. And now Alfonso is going to actually get into the details of how you do more interesting stuff with that, and you request and serve and fetch content from the network. So thank you very much, and happy to get questions now or at the end of the session.
I have a quick question. Talking about the implementation of Merkle DAGs, I mean, Ethereum has a similar implementation with Merkle Patricia trees, wherein, each node has its own data. So why isn't there a similar implementation to Patricia trees instead of Merkle DAGs in IPFS?
So you mentioned that in Ethereum is in what trees? I didn't get that.
Merkle Patricia trees. So it's sort of a modified implementation of Merkle Patricia trees, wherein each node, instead of saving the hash, has sort of pointing towards the actual data, and obviously it's referencing to them via hashes. So I just wanted to sort of draw a parallel between them.
Yeah, to be totally honest, I don't know the details of what Ethereum does and how the DAG is different there. But I don't know if Alfonso, but I'm happy to check and come back to that.
I think I didn't get the question right. So you're trying to understand what is the difference between the DAG as explained by Yanis and the Patricia tribe that it is implemented in Ethereum?
Yes.
So, from what I would have to check the details because it was a while ago, but from what I think, you're able to implement the Patricia tribe with our Merkle DAGs, because we are suggesting a general construction in which you could link in any way. So the same way, and actually this is something that I know that some teams have tried to use these same constructions that we propose with links and self-describing nodes, and have that same structure. So this is a general framework to build things like, for instance, the Patricia tribe in Ethereum.
Makes sense.
So what Yanis mentioned with IPLD, you could, IPLD in the end is a data model, a schema model. It has a lot of tools in order to, with that structure and leak data, be able to build the structures that you have in Ethereum.
Makes sense.
Great. There is one more question if we want to cover it now, which says, do you have this content add an additional overhead introducing delay? This is just the request from the network. So basically, you do that. It's the equivalent of, like putting the URL somewhere and asking the DNS to send it back to you. So I don't see how. I mean, it's a basic first step. So I don't know if you mean some other part of the sequence.
No, that's practically what I meant. But when I'm asking a query from a DNS, I'm getting it from a central response, right? The chances here are that if I ask for a content hash, I may not find it on the first go, or in my first query, the node may not respond, maybe because it's busy or something like that. In general, and if I'm doing that for, let's say, if I make a DNS query, somewhere down the line, it's cached for me where if I'm accessing the same, let's say if I'm having a video and I'm just streaming the video on an open connection, I'm not making repeated DNS queries. Whereas in a case where I'm doing it for a file that's divided into many parts and all of those are being accessed from different nodes, I do have some latency. That was the question. Do I have some latency there, rather, is the question.
Right. So you mean for subsequent parts, you have to go again through the whole system of, finding, like doing the content resolution, right?
Yeah.
Yeah. So this is correct. You have to basically trade off the benefits that you get from having content addressing and so on, with basically getting having to do this request multiple times. But as Alfonso is going to show later, you can bundle these together and send them using bitswap and a list of CIDs that you actually want. So therefore, it's not exactly that for every CID, for every chunk, you're going to send a separate query.
All right.
Does IPFS uses DHT? Yes, and this is this talk now is just going to go straight into the details.
I think let's jump into content routing, because all these questions are really related to this. As Yannis said, I mean, my name is Alfonso Larrocha. I'm a research engineer at Resident Lab, and we're working in all of this stuff that Yannis has explained. And in this model, what I'm going to try and share with you is how we find peers and content in the network. So really related with all of the things that you've been asking for. You can see my slides, right? You said you didn't double check.
Yes, it's totally fine. We can see.
Okay, perfect. So this is the agenda we're gonna follow in this model. First, a brief introduction. We're gonna go in deep again. We're not going to go in deep again between the difference of location addressing and content addressing, but we're gonna see what challenges we have when doing content routing in peer-to-peer networks. And we're gonna use this to build upon the content routing interface used in the P2Peer and IPFS. This content routing interface, what it will give is an interface in order to find content in the network and announce content in the network. And right now there are two main implementations for the content routing interface in the P2Peer and IPFS, which is the DHT-based content routing, that we're gonna see that it's an adaptation of the Catimlia DHT, and the gossip-based content routing that is implemented mainly with a PubSub algorithm and with bitswap, that is the main content exchange interface in IPFS. So let's jump into it. Here, what I wanted to try and put forward again is the main differences that we have between location addressing and content addressing, but from a finding content point of view. Because while in location addressing, what we're saying is to the DNS system, hey, please let me know for this name and this resource, where is this resource and who's the server that can give me this content. So it's tell me which server knows stores this file, and then the DNS system will point to the IP address in which that resource is stored and the path of the specific resource. If that resource doesn't exist in that path anymore, it means that I won't be able to find the content. This is not the case in content addressing, because in content addressing, what I say is, hey, give me this CID. I ask these questions to the network, and peers connected to me or even connected a few hops away will let me know if they have the content or not. And then eventually one, and potentially the one that is that is closer to me, will send me that file if it is storing it. So we see that while in location-based addressing, we have a central registry that knows how to reach every single peer and where the content is stored. This is not the case for peer-to-peer networks and in the case for IPFS. So we'll see that this is a challenge in order to find content in the network because there is no central entity orchestrating the storage and the discovery of content. There is no central directory to know how to reach every peer in the network. So someone may say, hey, I have the contents that you're looking for, but then we need to know how to reach that, that peer, and this may not be easy in certain cases. And then in peer-to-peer network, we face certain problems, like for instance, high churn, potential civil tax. So certain limitations that we wouldn't face when we are in a more centralized network or in a location addressable network. And we have to do this for thousands of peers and millions of content. So we kind of see the challenge of this. So the challenges applies to a lot of things, like, as I've said, discovering peers in the network, finding the peers that are storing that content, dialing those peers, so knowing how to reach those peers in the network, and doing it in a scalable way. Because as some of you mentioned, we have to do this in a way where we don't add a lot of overhead to find content in the network. And this, I mean, this challenge applies to this subsystem, the content discovery and routing system that I will be talking throughout this model. And we're going to start with routing and provider records. We'll see in a moment what a provider record is. The content routing interface in peer-to-peer and IPFS exposes three main operations. We have the provide operation that in the end what it's saying is, hey, I'm announcing this content to the network, so whoever wants this content, I just want to let you know that I'm storing it. We have the resolve operation, that in the end what it does is resolve what peers are storing the content in the network. So we're not requesting explicitly the content, we just want to know what peers are storing that content. And then we have the fetch operation, that is the one that explicitly requests the content. So once we found the peers that are storing the content, we explicitly request the download for that content. And this is basically the operations that the content routing interface exposes. We may need some additional schemes according to the content routing protocol that we use, because for instance, for the DHT, we may be able to find where the content is, but we also need to know how to dial the peer that has the content. So for this, we have another scheme that is that we call peer routing, in which we will have to not only find who's storing the content, but how to reach the peer that has the content. We'll see this in a moment. And the design goals that the content routing protocols that are embedded into this content routing interface need to have are, first of all, it needs to be reliable. So we need a way to find any content in the network and any peer living in the network so that we can fetch the content. It has to be scalable and fast. So the performance of queries should not be affected by the size of the network or the status in which the network is. And also ideally should be resistant to churn and civil attacks, so that, I mean, there's no way of abusing the system. And we'll see, as I've said, that in IPFS and EP2P, we currently implement two main approaches for content routing within the content routing interface, which is the DHT-based approach, which is implemented in the EP2P Kadimlia DHT, and then the gossip-based approach, which is implemented in Bitswap in one part, and then we can use PubSub algorithms also for this. But with this content routing interface, actually, we could leverage any other content routing subsystem, so we would be able even to use a centrally governed providing subsystems as DNS. I mean, we could think of IPFS and DNS attached to IPFS, so that instead of having to go through these decentralized protocols, we can go to a central system to request where the content in the network is. But this wouldn't make a lot of sense, right? So let's start discussing a bit the DHT-based routing. And before we start with this, let's do a small detour and explain what a peer is in the IPFS network. Because in the end, a peer is just, I mean, peers in the network is a node in the IPFS network, and they have a unique ID within this peer-to-peer network namespace. We'll see in a moment how this is formed. Peers run different services and different protocols, and other peers will be able to leverage these services and protocols. So if I'm running, for instance, the DHT protocols, or other nodes in the network implementing this protocol will be able to interact with me. And a peer has to always be routable and reachable in the means that it's possible, and it must be discoverable. And this discoverable part is the one that we mentioned before, and for which the peer routing scheme is responsible. And finally, peers, for the interaction between and the channels between peers use encrypted communication channels, because in the end, the identity of a peer is determined by a cryptographic key pair, like we're used in Ethereum. And from this cryptographic key pair, the ID is inferred. So this ID is the unique name for the peer, and is also used in order to establish the security channel between the nodes, between the peers a peer may be interacting with. So this is basically like the things that we need to bear in mind about a peer, that it has a unique ID, and there's and this unique ID is generated through a cryptographic key pair that is used to start secure channels between the different peers. And the DHT based, I mean, in the end, a DHT provides two-column table, a key value and a store, that is maintained by multiple peers. And the reason why we use this is a way to store routing tables in a scalable way in a peer-to-peer network. I guess many of you know how the DHT works, but in the end, in order to know the peer that is going to store a specific key of the DHT, what we do is to check the distance between the key and the peer. So if I have an ID that is QMXYZ, I know that I need to store the keys that has a lower and that are closer to me. So I will be storing, for instance, the QMXYA and all of the keys that are near my peer ID. The DHT in IPFS is used for several things. First of all, for peer routing. So we're going to store in the DHT a tuple where for each peer ID, we're going to store the multi-address of that peer. And in the end, the multi-address, it's a string determining the different ways and the different protocols that I can use to reach a peer. So for each peer ID, what we're going to find is like a string similar to the one that we see here, where we have IPv4, where we specify the IP, we specify that the node specifies that it can be reached through TCP in a specific port, and so on. So this is one of the things that we are storing in the DHT in IPFS. The next thing that we store is the provider records. The provider records in the end are pointers to where the content in the network is stored. And we will have a tuple in the provider records, which is the content ID and the peer ID. So the key is the content ID for a specific CID. We will have in the value of that row the list of providers that are storing that specific content ID. And also they are used for IPNS records that we're not going to discuss this in this session, but in the end, IPNS records are used to find mutable content in the IPFS network. And IPFS implements an adaptation of the Kadimlia DHT in which the address space is of 256 bits. So we'll see that every peer ID and every CID is 256 bits. Every key in the DHT is 256 bits long. And the distance in the Kadimlia DHT between the peer ID and a key is determined, or between different keys, is determined through an XOR of the two values. So if we get, in order to know how far I am from a key, I get my peer ID and I do the XOR with the key. I want to know how far I am from it. And the Kadimlia DHT implements the routing tables using trees. So we'll see, and this is, you can see here how the Kadimlia DHT routing table looks like, where we have a binary tree that is divided into different subtrees, and these subtrees, in the end, in the subtrees, what we're specifying is the different prefixes of the peers that are in that part of the tree. So if we want to look for a peer or a content in the DHT that is that has a prefix 0111, what we're gonna do is move into this part of the tree and look the list, because in the routing table I will keep what we call a bucket that in the end is a list of peers that share the same prefix. And if we want to find content that is near this prefix, what we're going to do is get the peers from this K bucket in my routing table and send parallel requests to all of them to check if they have the content that I'm looking for in the DHT. And if this is not the case, what they will do is answer me with a list of peers that are closer to the content than the ones that I have in my current routing table. So this is briefly how the Kademlia DHT works, which is the one that IPFS uses. Now we're going to move into providing content, which is like this provide operation that we use in IPFS, in the content routing interface of IPFS, to announce content to the network. In IPFS, content is not replicated or uploaded to any external servers. So the process of providing in the end is putting a pointer in certain peers saying that for that CID, I am the one storing that content. And in that way, I announce the content to the network. And this is the provider record. So in the end, if, for instance, I want to put content in the network that has a multi-hash H, what I do is look up the 20 closest peers to the CID H of the content I want to put in the network. And I put in these 20 peers, I put the provider record, which is this pointer in which the key is the CID and the list of peers is just me because I'm the one currently storing the content. So this is how we announce content in the network, putting a provider record in the 20 nearest peer to the CID of the content I want to announce. Provider records needs to be republished because they have an expiration. I mean, every 24 hours, provider records expire, and this is done in order to account for provider churn, because it may be the case where the 20 nodes where I've put my pointer to the content disappear from the network, and then the content cannot be found. So to prevent this, provider records are periodically republished. And also, this republication is done every 12 hours also to account for peer churn, because it may be the case that, I mean, I mixed here, we have provider churn and peer churn. The provider churn it means it's me, the one that can leave the network. So that's why I need to reprovide every 24 hours, because if not, the provider record expires. Because if I'm not republishing, potentially it means that I'm leaving the network, that I left the network. So it makes no sense to keep storing that pointer to my content or to the content that I'm storing if I'm not in the network anymore. So this is why provider records expire. And then we have the provided records republication every 12 hours to account for peer churn, which is the point, I mean, it is the moment where the peers where I put my pointer may leave the network. And also, if, for instance, another peer requests that goes to provider record and requests that content that is stored in my peer, they become from their own temporary providers. So they are added to this list and they can provide the content because they are storing it. And this temporary providing happens until there's a garbage collecting process, because in order for peers not to fill with content their data stores from all the content that they may be downloading from the network, when their data store of peers reaches a 90%, every 1 hour there is a garbage collection where the content that it is not explicitly pinned, and I'm going to talk about pinning in a moment, it is removed from the network. And this pinning process, to avoid this garbage collection from removing information from my data store, we have this pinning operation that in the end what it is doing is flagging the garbage collector not to remove that content, and also adding my peer in this pointer, which is the provider record, to let the network know that I will be storing permanently that content also. So this is how we can announce, or the different ways in which we can announce content in the network through the provide operation of the content routing interface. And then the same way we provide content, we can get content from the network, and getting content is really similar to putting content. In the end, if we're looking for this same HCID that I was mentioning, we can use the resolve operation in order to find providers for this content. And what we would do here is to request, we try to find these 20 nearest peers to the CID, and we are going to request the peer record from them. So we make this DHT work in order to find the 20 peers that may be storing my provider record. And when I get the provider record, I get a list of peers that are storing that CID. The problem is that when we receive this list of peers, in this list of peers, what I see is the peer ID, but I may not have the multi-address, this string, in order to know how to reach that content. In this case, what I may need to do is to, if in my routing table I don't have the multi-address for the peers that are providing that content, that are storing that content, what I may have to do is to perform another work in the DHT to ask for the information for that peer, so to perform the work for peer routing in order to have information about how to reach that content, that peer that is storing the content that I'm looking for. And in IPFS, we use two types of DHT because, if you include, of course, the DHT always finds content in the network as long as the peer is reachable. The problem is that in the IPFS network, there are a lot of nodes that may be behind the NAT and may not be easily reachable. So if we include records for peers that are not diable in the DHT, it means that when we're doing these works, we may end up always finding nodes that are not reachable. In order to avoid this, that it was penalizing the performance of DHT operations, in a recent update of the IPFS client, we added two different DHTs, a public DHT that in the end only includes publicly reachable peers. So you know that you would have a way of reaching these peers if you get the multi-address, and then a private DHT that only includes peers belonging to the same private network, so that we can make requests to nodes that are public and that we know that are public, and also to know, we can make operations in the DHT with nodes that are in our own local area network. Of course, the DHT, many of you may be aware of this, but they have their pros and cons. The pros is that it's fault tolerant, resistance to churn. It finds peers with 100% of probability as long as they are reachable, and they ensure the freshness of the routing information. But the problem is that when the network scales, they may be slow, and it may not be easy to announce all the content that a peer is storing or finding the content in a timely manner. And also there's another problem with DHTs, that is that DHT proximity is not the same as spatial proximity, because the DHT is building an overlay network over an underlying network. So when I say that I'm getting content from my DHT neighbor, it may not be my actual neighbor in the underlying, for instance, IP network. So it means that I may need several hops in order to get the content. And this may add an overhead that it wouldn't be the case if I ask the content from an actual network that may be near me spatially. And that's why, here I just wanted to share a few default configurations of the Katimlia DHT implementation in IPFS. Of course, because we have these limitations in the DHT, we also implement gossip-based routing approaches in order to overcome many of the barriers and the overheads that we may find in the DHT. And the gossip-based routing, it is implemented mainly through Bitswap. That we're going to talk in a moment about Bitswap, but Bitswap is the main content exchange interface, and it does gossiping content routing in which it asks its neighbors if by any chance any of them may have the content that I'm looking for, so that I don't have to resort to the DHT if some of them have already the content. And then we can also use PubSub. There are a few implementations of PubSub protocols in P2P and IPFS, like GossipSub, that is used by Ethereum 2.0. And with GossipSub, we would be able to organize different clusters and different swarms of nodes exchanging information about content that may be flowing in the network. And as I have advanced at the beginning, we could also use any other external subsystem and implement over the content routing interface of IPFS and P2P any other content routing subsystem, like for instance BitTorrent trackers. No one has done this as far as I know, but this would be possible. And so to summarize how content routing works in IPFS, because we've seen like the resolve part and the provide part, and we'll see the fetch in a moment. As Yanis advanced, you get a CID out of band, and the first thing that our IPFS client does in order to find the content for that CID is first use the gossip-based content routing. So it will ask the neighbors in case some of them has the CID that it is looking for. And if this is the case, the content exchange interface comes into action, but we'll see the content exchange interface in a moment. If this is not the case, what it happens is that we resort to the DHT in order to find the content. So we do this first walk where we find the provider records for that CID in order to get the list of peers that may be storing that content. And then we may need to do a second walk in the DHT in order to find the information about the peer that we want to fetch the content from. And this is basically how content routing works and the content routing interface works in IPFS. I don't know if there are questions and if we have time. If this is the case, we can move into the content exchange interface.
During content routing, doesn't it become very easy? Because if I know how to move throughout the dynamic hash table and figure out what fragment of a file is located in which peer, doesn't it become very easy to sort of censor any sort of file that I do not want entering into my network?
So it is not that easy, because the same way that I mean, it depends, of course, if you're the only provider, but your 20 nearest peers to that content are not the 20 nearest peers for another peer in the network. So if more than one node that is trying to provide that content, it means that the provider record will be spread into not only the 20 nodes that you think are nearest to you, but 20 nodes that are nearest to the peer, I mean, from the view of the other peer that may be providing the content. I don't know if that answers your question.
I see. But
we have, I mean, when I say closer nodes, it's within your routing table, and you do a walk, and your walk may not be the same. So it's not deterministic. Your work may not be the same as the work from another peer in the network.
Makes sense. But if it's still entering my network, each file is still deterministically hashed. Yeah. So if it's entering my, if I just set up like a packet sniffer which checks whatever the packets that are entering my system, I can just hash them and see whether or not the hash matches the one that I'm trying to censor.
Yes, but then, I mean, that's why you have the DHT approach and the gossip-based approach. Then if I have neighbors, and the PubSub approach, in which even if you try to do this Eclipse attack, where you're trying to censor my peer, you don't know if I have additional networks and I'm not using the DHT in order to find that content, and I'm not using any other content routing approach.
Makes sense. Makes sense.
We're gonna see in a moment. I mean, this will make a lot of more sense once we see BitSwap, because in the end, BitSwap, what it does is doing this. It orchestrates this gossiping while it requests a list of providers from the DHT. So it's hard to do an Eclipse attack when you don't know the actual connections that a peer may have.
Yeah.
Makes sense.
Yeah, so I think we have covered a lot of material in this 1 hour. I just wanted to say that, any of you like have any questions that you think, like, even if you think they're noob level questions, feel free to ask them, because it's important that, you at least get a base for the motivations of all this. So, really feel free to ask whatever questions you might have popping up.
Yeah, so hello. So IPFS, how IPFS is different from torrent or BitTorrent?
In in several ways. I'm gonna. I mean, I don't want. I don't know if
I just want a brief, I know idea,
Yeah.
because we have all been using torrent. So it's like,
Yeah. So first of all, the content routing approach that Torrent uses, it's based in trackers. So it uses DHT, also DHT in order to find peers in the network, but content is found through trackers, and trackers are kind of centralized. I mean, you have to have a tracker server that gives you the list of peers in the swarm that may be storing that content. Also, content in the BitTorrent network is not self-describing. So like when you get these magnet links, you get what you're getting is a list of peers that may have that content, but the content is not verified and checked, as Jens have explained in several cases. And this is the reason why sometimes you may be looking for a song and you end up having another song that is completely different, because it checks like the name of the file and not the actual content. And maybe there are a lot of other things, but I can't come up with them.
no, yeah, I got it. And is there any incentives for the providers to provide content?
There isn't currently. So this is let's say a best effort network.
So for torrents, there is one certain incentive wherein, let's say, if, as you said, there are certain swarms, there is a sort of a fee wherein you can join these private swarms where you have specific files that are hosted, maybe some new episodes for a latest TV series, and you have these private swarms that you can join and then get seeded those latest files. So, I mean, there are certain incentives. It's similar and very dissimilar at the same time to Filecoin, but yes.
Yeah, and also in BitTorrent, it's true that you have, for the exchange, you have the tit for tat. So you have to have contribute with upload bandwidth in order to get the same download bandwidth or equivalent. And this is not the case in IPFS.
Okay.
But that's also not necessarily required. I mean, if you use a certain client in which you can change the upload and download speeds, then you can actually get away with that too.
Okay, if there are no more questions and we have like 20 minutes left, 20 minutes more, we can go into the content exchange interface. Because I know that we are on time, but if you don't mind, like being 20 minutes more.
Sure. Let's go ahead.
Great. So, we've seen how content is represented in the network. We've seen how to discover content in the network. Now we're going to see how to fetch content from the network. We can, with content routing, what we get is the list of providers that may be storing that content, and then we have to request the download of that content. And this is done through the content exchange interface. And here, the two main protocols implemented in this interface are BitSwap, that we've introduced it a few times in the previous model, and GraphSync. That GraphSync is used for one-to-one stream exchanges. We'll see this in a moment. And of course, we're gonna talk about this content exchange system. So we are moving towards the end of all of the IPFS system components. And we're gonna start with BitSwap. BitSwap has this modular architecture. It's a message-oriented protocol to exchange blocks in a peer-to-peer network. BitSwap is used in IPFS, but it is also used in Falcon, and it may be used in isolation with any other system because it's a general protocol. And this is the architecture that it has. It exposes a protocol interface with two main operations, which is a get operation that in the end it's saying, hey, nodes in the network, please get me this block with this CID from the network. And then we have the put operation, which is just an announcement to all of the nodes in the network that I am storing that specific block with that CID. And the models that comprises Bitswap are the following. First, a connection manager, because what Bitswap does is leverage the actual connections that the peer may have. So the connection manager, what it does is to use a network interface in order to interact with other nodes in the network and orchestrate the exchange of messages with other nodes in the network. Then we have the ledger. And don't be confused, ledger not in a blockchain point from a blockchain point of view. This ledger is just a data store that tags the, so when my peer, for instance, start getting requests from other peers in the network, I track this want list of other peers, so the CIDs that other peers may be looking for, in case I can't respond successfully to that request. So in this ledger, in the end, what we have is data store with, for each peer, the CIDs that he's looking for. And the ledger communicates with the block store, because in the block store, I'm storing the blocks, the different blocks that, and the content that I provide and that I'm storing. So if at one point in the ledger, I see that the ledger sees that I'm storing a block for the CID that other peer may be looking for, it serves straight away that block to the peer, to the requesting peer. And finally, we have the session manager. And the session manager, I mean, every time that Bitswap starts and tries to find content in the network, it triggers a new session. And the session manager, what it does is just orchestrate all of the sessions and all of the different streams of discovery and download of content in the network. And the session manager leverages the content routing interface that we mentioned in order to find additional providers for the content. So we'll see that Bitswap uses a gossip-based approach in order to find content in its neighbors, and also uses the content routing interface to use the DHT, DNS, network database, a PubSub algorithm or whatever to find additional content in the network for the case in which its neighbors doesn't have the content. And let's see how Bitswap works with a brief example in IPFS. So whenever we want to find content with IPFS, we say get and the specific CID for the content that we're going to find. And what IPFS does is first check its block store in case it already has some blocks of the content that it's looking for. And if this is not the case, or in the case that it's just a bunch of blocks and it needs to find more from the network, it triggers a new session in Bitswap to get the blocks pending for that content. Bitswap is a message-oriented protocol, and we're gonna see 6 different messages in Bitswap. 3 request messages, the one half message, the one block message, and the cancel message. In the one half, what we're saying is, hey, other nodes in the network, please let me know if you're storing that block, but please don't send it to me. Then we have the one block that is saying, if you have that block, please send it to me. And then we have the cancel that is, I'm not looking, I mean, this is set, we'll see in a moment, but the cancel is sent after we've sent a request, and it's saying, hey, I don't want this content anymore, this block anymore, so remove it from the ledger, from my want list, because I don't want it anymore. And then we have the responses. To the one half, we may respond with a half, saying that we have the content. To the one block with the actual block, and to the one half and one block request, we may receive a don't have response in the case where the node doesn't have that specific block or the content that I'm looking for. And I don't need to go through this again. I mean, Bitswap understands content the same way that the rest of the IPFS network understand content, but this is important for the case in which Bitswap is not used in IPFS and it's used in other systems. For Bitswap, a file is chunked in different CIDs, and these CIDs are organized in a tag structure, as Yanis have mentioned. And why this is important? Because the operation of Bitswap depends on the way in which the orchestration of content discovery and content exchange works in Bitswap depends on the request pattern that we may be using to find the content. Because usually in IPFS, we have two main request patterns. The first one in which we try to download a full DAG structure, like when we try to download a full directory, a full file, a full data set, where what it happens is that, let me take the pointer, what BitSwap will do in this case is that as we want all of the levels and every block in every level of the DAG structure, BitSwap will ask for the CID root in order to get the links for the next level. Then it will have to ask for the blocks in the next level to get the links for the following level, and so on back and forth until it gets all the blocks for that DAG structure that comprises the content. And then we have another common request pattern, which is the one that we use when we render, for instance, a website in IPFS, where what we do is access the content through a path. And we say, hey, we want to render the web/page/doc.html. And in this case, we don't want to download all of the nodes and all of the blocks in that DAG structure. We only want to download a specific part of the DAG structure. And in this case, what BitSwap will do is that it would get the CID root for that DAG structure, get the link that we're interested in. So it will check and it will go to web, get the block for the next level, and so on until it follows the path and it gets to doc.html. And in this moment, it would get all the links and fetch all the blocks for all the files. This is important because this request pattern determines the back and forth of messages that BitSwap will follow. And whenever we want to find content, as we said, we trigger a new session. And when we trigger a new session, the first thing that BitSwap does is to broadcast a message to all of its neighbors. So BitSwap will do a broadcast sending a 1/2 message for the root CID, so for this first block, to all of its peers. And in parallel, it will perform a walk in the DHT for the case in which none of the neighbors have that root CID, and in order to populate the session with peers and potential providers for the content. When the peers, my neighbors, or alternatively the providers answer saying that they have, or the DHT walk answer saying that there are nodes in the network storing the content, what it happens is that they will answer with a 1/2 message. So here the walk of the DHT finishes and I get a bunch of peers that may have the content. And also we get 1/2 messages from my neighbors that have that content. This is the view from my side, that I'm the requester, and the view that peers that are receiving these requests have is that I may be sending, for instance, 1 messages for different CIDs. This is me, peer A, and this is the peer B receiving request from me. I may be sending 1 messages from my peer, and what peer B will do is that for each new request, it will update the ledger that I mentioned, this data store that stores my want list. It will update with each new request my want list, so that if at one moment it receives by other means a block, it can send it back to me and remove it from the want list, because it means that if it's in the want list, I'm still looking for it. So yeah, and this is this is the view that the peer receiving request will have, that in the end is just updating the ledger, and according to the moment I receive the block, send the block right away because I'm interested in it. And so we said that when we trigger this session, the first thing that we do is broadcast a bunch of 1/2s to all of our neighbors, all of my current connections, and I will receive 1/2 messages from different peers. The moment I receive 1/2 message, I right away send a 1 block for that CID to the peer that answers successfully, requesting the actual download of that block. And in the meantime, I may be receiving 1/2 messages from other peers that have more latency to me. And I will accept all of these 1/2 messages, because now what I'll do is that I don't request the block, I just get the block from peer B, but I will add to the session. The sessions keep a list of peers that have answered successfully to the broadcast phase, to the moment that to the request for the root CID. And the reason why we keep all of the peers that may have asked successfully for the roots ID is because from there on we are not going to interact with all of our neighbors, but we are going to only interact with the peers that have answered successfully to the roots ID, because they most potentially will have the rest of the blocks of the content. So it makes no sense to interact with peers that have not answered or that have answered with a don't have for the root CID, because they potentially won't have the rest of the DAG structure. So we sent this first broadcast. We now have a list of peers of that a list of peers that are storing the content. Someone has sent me the root CID, so now I inspect the links of the root CID and I get all the blocks in the next level. So if we go to the DAG structure, we get the blocks in the next level. And in the next request, what we do is directly send a request to the peers in the session, to one of the peers in the session with a want block, directly with a one block for the blocks in the next level. I will keep like sending, I can even send non-overlapping requests to the different peers, to peer B, C, and D, always to peers in the session. And I may be getting responses with halves, don't halves, or the blocks. And one thing to note is that if one peer answers unsuccessfully to several of my requests, I will remove him from the session. And if at one point I run out of peers in my session, what I need to do is to walk the DHT, Bitswap walks the DHT in order to find another bunch of potential providers. So in this way, we will be like traversing the DAG, sending these requests to the peers in the session. And if we run out of peers in the session, we need to go to the DHT. And finally, this cancel message that I mentioned, every time that a peer receives, so for instance, if I'm peer A and I've sent a bunch of requests to all of my neighbors or to the peers in the session, and at one point I receive a block from one of the peers, what I do is send a cancel message to all of the peers in the session to let them know that I don't want that block anymore, in order to avoid peers sending duplicate blocks or someone sending me a block that I already have. Because in this way, we make a more efficient use of bandwidth. I see a question in the chat that say how peer broadcasts. One thing that I mentioned is that, I mean, IPFS nodes keep established connections from previous interactions with other peers in the network, because due to DHT lookups, due to other Bitswap sessions, and so on. So what Bitswap does is leverage the established connections that a peer already has. And if you join the network for the first time, an IPFS peer has several ways of finding peers in the network and establishing connections. Like for instance, MDNS in the case of local peers, it can use a bootstrap and so on. But in the end, Bitswap, what it uses is the current established connections that a peer may have. That's why in this model, like in this architecture, I said that the connection manager leverages whatever network interface is available in the network, because it leverages the current connection with other peers or with other providing subsystems in order to forward this broadcast. And this is it for Bitswap. I don't know if there's any question. Let's stop here to see if there are questions around Bitswap, and if not, we move into GraphSync.
Hey, Alfonso, there's a couple in the chat.
Yeah, so I think I covered, let me know, Niraj, if I haven't covered the one for the peer broadcast. Cool. And then you can also use a modified client to just lie to the tracker. Oh, okay, and this is just, thank you. Something related to our discussion, our previous discussion.
Okay, great. Looks like it was covered.
Cool. Then let's talk about GraphSync briefly, because like with Bitswap, what we've seen is that Bitswap has the gossip-based content routing asking its neighbors, and it leverages the DHT, and then it requests content block per block. With GraphSync, what we have is a request response protocol that is used to synchronize graphs across peers. So here we are not going to ask the network for the content and get the network block per block. What we're going to do is contact a peer that we know that it has the network, open a stream, and get all the blocks at once through the stream for the content that I may be looking for. And this is done through IPLD selectors. We've seen that IPLD is this data model used to represent DAGs and so on. And one of the models that IPLD adds, it's a few selectors, I mean, a full selector language, to be honest, that allows you to make requests and complex queries over DAG structures. So here we see that instead of asking block per block, what we will be able to do using GraphSync is to make some selection, use a selector to say, for instance, hey, I want this specific node, or I want this branch of the DAG structure, or this branch of the DAG structure, and just this leaf of the DAG structure. With this IPLD selector, what we will be able to do is to make these complex requests. And the operation of GraphSync is really simple. In the end, it's a request response protocol where in the request I send to the peer I want to get the content from a single CID or a selector and some metadata of how I want to open the stream and the data channel. We open that data channel, and the other peer will open if it accepts the request, it opens streams and send all the bunch of blocks that I may be looking for right away. So we see that instead of asking block per block and having to traverse the blocks one at a time, like in Bitswap, here what I'm saying is, I know you have the content, I want to synchronize with this DAG through this selector, so please send me all of the blocks that I'm pending from this DAG structure. And actually, this is the protocol. I mean, in IPFS is used to exchange one-to-one protocol, and in Filecoin is used to, for instance, exchange user data in deals, and also to synchronize the chain. And to wrap up, let's have a quick comparison of GraphSync and Bitswap, but actually I've introduced all of the concept. While Bitswap is a message-oriented protocol, GraphSync is request response. The content exchange in Bitswap is block by block, and in GraphSync is through streams. When you request content in Bitswap, you use a CID or a path to get the content, and in GraphSync, you perform a complex query through an IPLD selector, and this means that as Bitswap adds content routing to the protocol, you can have multiple paths of download. We saw here that if we go here, we could be asking for different blocks to different peers, and this is not the case in GraphSync, where it's a one-to-one protocol. And finally, like, the use cases are pretty, they are related, but also different in the sense that they're both used for file sharing and download. They're used for exchange of data, but GraphSync is used for the case where you know that the other peer has the content and there's a large amount of data that you have to download. And then Bitswap is really useful to accelerate content routing, because as you can ask your neighbors and you can traverse your own DAG without having to depend on the other peers, it makes it really suitable for certain use cases where you want to be fast and like have several ways of download content. And this is all from my side. I don't know if there are questions or something else that you want to discuss, but this is all that we wanted to share today.
Fantastic. Thank you so much, Alfonso, for joining, and also Yanis, who had to leave at the hour. Everybody, please feel free to ask any more questions if you have. Otherwise, we'll close it out with Alfonso. If there are no more questions, you can probably go, and then we're going to have pointers to next bits of curriculum and an assignment, a mission for you all. Cool, and we'll collect any other questions async. Feel free to keep asking in the Discord, and we can share them back for Alfonso and Yanis to provide answers for.
Thanks, Alfonso and Dietrich, really for putting this together. It was a really cool introduction to IPFS, and I think after this, when they go through Proto School as well, then they'll really solidify much of the concepts that they have covered here. then they can always refer back to this since we have streamed this. So yeah, you can always refer back to this.
Great.
Yeah.
Any question? If not, thank you for having us here. And
yeah.
I hope you have a blast with the Wake 3 stack.
For sure, for sure.
Thanks, Alfonso. See you.
Bye-bye. Cheers.
Thanks, everyone.
All right, so
Thanks.
I'm gonna, so hi everybody, I'm Dietrich. So that was Alfonso and Giannis. They're from the ResNet Lab team at Protocol Labs. I work on the ecosystem team, do stuff related to IPFS and Filecoin and P2P, and help hook up groups like yours with some of the talks and the engineers that are part of these projects and technologies. So I really thanks for diving deeply into IPFS today. You know, as Denver said, there's an assignment with each one of these things and also some follow-up reading material. So let me share a screen real quick and I will introduce you to some of this material real quickly. We have a website that was developed by a team at Protocol Labs called ProtoSchool. And ProtoSchool is a set of interactive tutorials that you can follow. These cover a number of different topics. Some of them are the fundamental principles underneath or on which that technologies like IPFS, libp2p, and Filecoin are built. Some of them are explorations of the APIs that these technologies have. For the purposes of this assignment for today, I think that the Denver said the most valuable one would likely be for IPFS in the IPFS course, focused on understanding the files API. So if you go to this URL, which I will drop in the chat here. There we go. This is probably the most important tutorial for the assignments and applications that you all will be building. This explores the basic files API of IPFS. So ways to add files, ways to read the contents of a file, some of the basic file system operations like reading a list of files in a directory. This is probably the best place to get started for a programmatic introduction to IPFS APIs. Each one of these sections, they have an interactive JavaScript tutorial that you can run in the page. So there's no infrastructure to set up for you in order to walk through these tutorials. So this is the place to get started. For today's assignment, however, your goal, your mission, should you choose to accept it, is to post a selfie or a photo that you prefer into the general channel, or you can DM it to me, post it to IPFS, get the CID. So you learned about CIDs from Giannis and from Alfonso today. That's the address to the file that you're going to post. You can do this programmatically using these files APIs from this tutorial here. You could install IPFS desktop and drag and drop, upload it that way. You could post it through Pinata or Fleek, a number of different services that allow you to host IPFS content. You can spin up your own Go IPFS daemon on the command line and add the file through there using this IPFS CLI. All of these are detailed in the IPFS docs website, which is docs.ipfs.io. There's a number of different ways. It's up to you which way you upload a photo, but upload a photo, ideally a selfie, send me the CID on Discord or post it to the channel and flag me so I know that it's there. And then we'll put all those together into a class book of all of you on IPFS that you can share and take screenshots of and see who is all part of these cohorts. So that's the mission. That's the assignment. Doesn't matter which way you upload it. Just got to give me a CID to a photo, and then we'll put them all together. So thanks again for joining. Denver, let me know if there's anything else. I'll be around on Discord for the rest of the day. Also, you can join the IPFS community at the pound IPFS on Freenode on IRC. It's also pound IPFS on Matrix as well. So you can join either one, and those are bridged. So you can use whichever you choose. And we also have a forums at discuss.ipfs.io. So these are forums that are really active. These are great places that you can ask a question, and a lot of the IPFS community will come in and answer. Additionally, if you have other development questions, we keep a very close watch on questions asked on Stack Overflow that are tagged with IPFS. So you can go onto Stack Overflow, ask a question, tag it IPFS, and usually we try to get back to those within a day or two.
Amazing.
All right.
Dietrich, just one question here. So
Yeah.
before they go through this regular files API tutorial, do they need to, like, is just going through this tutorial enough, or do they need to go through any other tutorials for background?
So that's probably the most important one for the purposes of what you all are learning. It looks like in this fellowship program. All the rest, a lot of these only take like 15 to 20 minutes, sometimes 30 to 45 minutes for some of the longer ones. It's well worth, I think, walking through the entire IPFS course if you have the time, given that this is it's already nighttime where you're at. The most important one that we talked about was probably this files API, since it'll give you a good introduction into the basic operations that you'll be using. But absolutely, if you have the time, walk through the whole IPFS tutorial. It's a series or a curriculum. It's a series of these tutorials. None of them take very long, but it will help fill out your education in terms of understanding what some of these basic concepts are, being very familiar, getting to the point of familiarity using a lot of these basic operations, being able to work directly with content addresses, and understanding how to work with larger data sets as you start to move into more complex and sophisticated applications.
Perfect. And just a quick question here, that so I also wanted to just give them a background about how this integrates with Filecoin, because it's how like Filecoin and IPFS are related. Probably you could just shed some light on that.
Yeah. So I can give a quick summary before we finish up here. So IPFS is an addressing protocol, content distribution protocol. As you learned today, the ability to address something by content means that you can get that content from anywhere, because you can trust that the data you receive from that address is the data that you asked for. It's cryptographically verifiable in that way. However, one of the things we also learned today is that you need to host that content on IPFS through certain means, whether that's an IPFS daemon that you run. You can use external services. We call them pinning services, to be able to pay somebody else to keep your content up on IPFS. If you publish a file to IPFS on your computer, and then you shut your computer down, that content is no longer available if you're the only one serving it. So that is something that Filecoin is a way to close that gap. You can pay Filecoin miners to keep your content alive and available on Filecoin. There are tools like Textile made a tool called PowerGate that allows you to add files through IPFS and have them automatically saved back to Filecoin, and be able to address them through IPFS and pull them out from Filecoin. Filecoin just launched in the fall, so a lot of the middleware application technologies that are on top of Filecoin that are connecting these things are still pretty new, where we're still working out, and the whole community is working out what the best workflows for some of these things are. But I think the best way to think about it is the same way that you might register your own domain name and then pay Amazon to host those files. With IPFS and Filecoin, you can add files to IPFS and pay Filecoin miners instead of having to commit to, say, one business like Amazon or Microsoft to host your files. With Filecoin, you can pay a marketplace of different people to be able to meet different use cases or needs you have for file storage. And so that's maybe the simplest way to describe what that relationship is there. I see a question down here: do the miners dictate the fees or the network? It kind of depends. I think the miners can say what their fee is, and it might correlate to different uses and use cases that you have. The way that Filecoin works is you propose a deal, and with that deal, you can say, here's how much I want to pay, and here's how long I'm going to store it for. Miners can choose to not to accept or not request the deal. So eventually, that community starts to find an equilibrium of what the cost is that people want to pay. You also might have different requirements. Let's say you are based in Europe and you have various different or specific regulations that you need to adhere to in how data is kept. Say it's something like medical data that has different geographic restrictions based on the regulations of the country that you're providing services in. You might need miners that operate in that country in order to make sure that the data is kept in the correct way. So those are different places where miners provide features that might have different costs than just generic storage.
Fair enough. So that was really awesome. I think in the coming days, they'll also learn a bit about ceramic and Fleek independently. So that will also be cool. Don't plan to dive into textile too much. But then I think having ceramic and Fleek kind of covers that anyway. So
yeah, there are a lot of different tools and services. The Fleek has also now released a tool, a service called Space that allows also easier bridging between IPFS and Filecoin, so that you can publish to IPFS and have that data backed up to and served from Filecoin.
Brilliant.
I think just a few days ago, actually, maybe late last week.
Yeah, amazing. And yeah, really exciting to learn about all of this technologies from the folks who are building it out. Thanks for.
Well, come join those communities, because it's not just Protocol Labs. There, textile, Fleek, and ceramic are all contributors to that community and help us figure out what these next versions or changes to the protocol needs to be. What are the things that they've built on top that maybe we should fold back into the core protocol as it grows and develops over time? So as you're building things, definitely come to the forum, come to to Matrix and hang out and talk, ask questions and provide your feedback, because the things that you're building and your contribution back to these technologies, that what makes them better is understanding what was easy, what worked, what was difficult, what was hard, what did you try to get working and you just couldn't. Those things, what was the killer part of it that really helped your Web3 application? These are the things that are super helpful for all the community to know. So come join in and hang out.
Perfect. Thanks a lot, Dietrich, for taking the time to put all of this together and making it yourself. Really amazing.
Nice to meet you all. I will see you all on Discord. Send me your CIDs and then we'll put them together.
Sure, for sure. Thanks, everyone. Thanks, everyone, for joining in. Bye-bye. Yeah, folks. So this week, we'll put out a doc covering everything, but then this week will mostly be focused on decentralized storage. The first part will be IPFS, there'll be ceramic, then there'll be Fleek. Then the second half will be on, we'll probably learn a bit about the graph protocol and something similar, covalent. So that's mostly the agenda of the week. And any questions or any thoughts, or we can just wrap up the call. Yeah, NFTs, we need to find time for that. So even this would take a lot of things, but if we have the time at the end of the week, we can include NFTs too. Is there anything else anybody would like to touch upon? Like, I think we have mostly, after this and NFTs, we'll mostly have covered everything that's part of the ecosystem. All right.
Denvo, like further regarding the Etherpunk project, that feedback. So would you be like giving us like feedback for that Etherpunk projects?
For the Etherpunk projects, like we already had the session in which you got the feedback. Right?
Yeah, like it was just like 3 minute session, not so we couldn't even like for even like our project Demon, we couldn't like explain it clearly. We couldn't get the proper feedback and all that one-to-one. So maybe we can do it on a Discord hangout.
Yeah,
like what we plan to do with it and what we're like thinking of, stuff like that.
Yeah, it would be a bit difficult to arrange sessions for everybody, but because then everybody wants feedback, then again, it would take a lot of time. Maybe the specific thing that you want feedback on, just put it on, on the Discord, and yeah, maybe you can tag Anudit, and whenever Anudit is free, he can take a look at it. Can have other mentors also take a look at it.
Most definitely.
Yeah.
Okay, fair enough.
Yeah. Thanks everyone for joining in. Bye-bye.
Yeah, thanks, Janvo. Bye.
Bye, Denver.
Bye.